Bismillahirrahmanirrahim. Dear students, class second year. This is lecture number 52, and we are talking about the alcohols. In the previous lecture, we completed the preparations of alcohols. Now we start reactivity. Reactivity of alcohols. Now alcohols with other reagents due to the breaking of yesterday I told you there are two kinds of the bonds involved in alcohol. There are two kinds of bond. One is a carbon-oxygen bond and other is the oxygen and hydrogen bond. So two kinds of reactivity give alcohol. When the cleavage of carbon-oxygen bond involved and when the oxygen and hydrogen bond is going to be involved for the reactions. The breaking of carbon-oxygen and oxygen-hydrogen bonds. This breaking of the bond depending upon the nature of attacking reagent. Cleavage of breaking of carbon-oxygen bond and oxygen-hydrogen bond depend upon the attacking reagent. If nucleophile attacks the carbon-oxygen bond is going to be broken down. Carbon and oxygen bond means this is the alcohol. This is alcohol, and if you are using attacking group as a nucleophile, then this carbon and oxygen bond is going to be broken down. So means you will get alkyl group and OH is going to be substituted. So this is the one condition. This is the one condition that when the nucleophile is going to be added, the carbon-oxygen bond is going to be broken down, means the hydroxyl group is going to be removed from the alcohol. So when electrophile is going to be used here, then the oxygen and hydrogen means proton is going to be removed from here like this. So oxygen and hydrogen bond, this is going to be removed like this. So this is the hydrogen is going to be removed from here. So ethyl ethoxy or alkoxy, and here alkyl group, and here is alkoxy. So it is going to be formed here, and the proton is going to be displaced or removed from the alcohol. So two conditions we have here. One is when the carbon-oxygen bond is broken down in presence of nucleophile and oxygen and hydrogen bond is broken down to form alkyl group. So the order of reactivity of alcohols with respect to cleavage of carbon-oxygen bond. Order of reactivity. In this case, tertiary alcohols are most reactive. Then secondary alcohol, then primary alcohols, then methanol. So when you are using nucleophile, and you are going to react the alcohols, so tertiary alcohols are most reactive. Then secondary alcohols, then primary alcohols, then methanol. So tertiary alcohols are more reactive than secondary and then primary alcohols. But in order to reactivity of alcohol with respect to oxygen and hydrogen bond breakage, then this process is reversed for this one. Then methanol is more reactive. Then primary alcohols, secondary alcohols, then tertiary alcohols, like this one. Methyl alcohol, primary alcohol, secondary alcohol and tertiary alcohol. So this is the nature of the reactivity of the alcohols when you are using nucleophile as a reagent. Nucleophile, nucleus slurring, maybe negative charge, maybe more electrons, just like water and ammonia. Electrophile, deficient, electron deficient, positive charge. So in the case of nucleophile, the carbon-oxygen bond is going to break it, broken down, and alkyl group is going to form, and OH is going to be removed, and tertiary alcohol will be most reactive, and primary alcohol will be the least reactive, and methanol. In the case of electrophile as a reagent, then the methyl alcohol will be the most reactive, and tertiary alcohol will be the least reactive here. So this is the condition of the reactivity. Reaction in which carbon monoxide CO bond is broken down. So these are the reactions given here. So we have many examples for the chemical reaction. Here the carbon oxygen bond is going to be broken down here. So if you see examples, now in which carbon oxygen bond is going to be broken down. So you have a methyl alcohol, methanol plus HCl, zinc chloride, heat, you will get methyl chloride and water. So this is going to be broken down and the hydrogen is going to be attached here. So in this reaction you are seeing that OH group is going to be removed from the alkyl. So this is the cleavage of the carbon oxygen, and in this case you use the nucleophile as a reagent. Nucleophile is going to be used as a reagent here. And there are other examples also. Yes, there are other examples also. Alcohol, alkyl alcohol, methyl alcohol, ethyl alcohol, and you are going to use a phosphorus, bromide in presence of nucleophile. Then alkyl bromide is going to be formed here, and phosphorus acid is going to be formed in this case. So again, this bond is going to be broken down here. This is another reaction to break the bond. You can use also phosphorus triiodide in this case also. So these reactions in which the OH whole group is going to be displaced, then you will see that in presence of nucleophile. Now the reactions in which the alcohol C oxygen and hydrogen bond is going to be broken down. in which the oxygen and hydrogen bond is broken down. So we will see another reaction here. For this purpose, you can see this one. These are the two examples I gave you. For this 3 examples, you can write phosphorus iodide also here. Then I will explain one test will be given in your short syllabus. So now the bond is going to be broken down to form a alco oxide. Means this hydrogen bond is between oxygen and hydrogen bond is going to be broken down in the presence of electrophile. So this is the and in the previous also there is a formation of the salt. You can put the sodium hydroxide or other you will get also this one. So this is a ethyl alcohol plus sodium metal. So this hydrogen is going to be displaced. Means the bond between oxygen and hydrogen is going to be broken down, and you will get sodium ethoxide and hydrogen gas like this one. So here in this case you are seeing also the between oxygen and hydrogen bond. This is in the presence of electrophile. In the presence of electrophile, oxygen and hydrogen bond is going to be broken down by the sodium metal, and you are getting the nucleophile sodium ethoxide or ethoxide, alcoxide you are going to be get, and hydrogen is going to be liberated here. This chemical reaction showing that the bond between oxygen and hydrogen is going to be broken down. So this example of the breaking of the oxygen and hydrogen. Now students, we have chemical reactions are here. Oxidation of alcohols. The second topic is oxidation of alcohols. Yes, if you see 5, page number 190. Oxidation of alcohols after reaction of with the OH is broken down. See how we done this one, and you can see the chemical reactions also here, and there are some oxidation reactions that we call catalytic oxidation. In the presence of catalyst, the chemical reaction is going to be carried out. We call catalytic oxidation. So in the catalytic oxidation, when you use the ethanol, here ethyl alcohol, this is the nascent oxygen, newly prepared oxygen. We call it nascent oxygen. So this nascent oxygen is potassium dichromate, concentrated sulfuric acid. Potassium dichromate and concentrated sulfuric acid, they are going to react to give a nascent oxygen, and alcohol is already here. So in this case there is a dehydration, removal of water, and this nascent oxygen is going to be attached with carbon here. So dehydration taking place, and the new functional group is going to be formed here. So this is the aldehyde, ethanol, and water, or we can say acetaldehyde. Acetaldehyde is going to be formed here, and from the alcohol by using a nascent oxygen, potassium dichromate sulfuric acid must concentrate it. They are going to react to give a nascent oxygen. This nascent oxygen is reacted, dehydration taking place, and you will get a new functional group which is called acetaldehyde and removal of the water. This is the first case. Then this is going to be if you are going to be carried out this aldehyde more react with nascent oxygen in the same conditions. This is the aldehyde, and this is going to be added here, and you will get carboxylic acid. Acetic acid, ethanoic acid. So you can prepare ethanol, and continuation you will get the acetic acid or ethanoic acid. You can get this. So these are the two chemical reactions in which you are getting aldehyde as well as you can get the acetic acid. Okay, if you use this is the primary alcohol. If you use this is the primary alcohol, but if you use secondary alcohol, this is a secondary alcohol, isopropanol. Isopropanol secondary alcohol is here. Nascent oxygen, potassium dichromate, concentrated sulfuric acid. So dehydration taking place. In the case of dehydration, this hydroxyl group and OH, and this oxygen is going to be attached here like this. So you will get another functional group. Ketone. Propanol. Propanol or ketone is going to be formed in this case. So potassium dichromate, sulfuric acid, 50 degrees Celsius, you will get a ketone in this case. So this is the secondary alcohol. Primary alcohol gives the aldehydes, and further there is a catalytic oxidation to prepare the carboxylic acid. In the case of the secondary alcohols, same conditions, 50 degrees centigrade, you will get the ketones and other functional group. Now tertiary alcohols. Reactions with tertiary alcohols. Dear students, here the very important condition written here. Tertiary alcohol is not oxidized by alkaline potassium permanganate when heated with a mixture of potassium dichromate and sulfuric acid. There is no oxidation. Tertiary alcohols resist to oxidize. They are going to be resist to oxidize in the first step, dehydration taking place. First dehydration. This is a tertiary alcohol. 1, 2, 3, 4. 2-methyl 2-methyl and 2-butanol is a tertiary alcohol. So I told you in the tertiary alcohol there is the first dehydration in the presence of concentrated sulfuric acid. In the presence of concentrated sulfuric acid, there will be a dehydration, removal of the hydroxyl group and hydrogen to make alkene. So alkene is going to be formed first. There is the formation of alkene. Like this. So this will be 1, 2, 3, 4, 2-methyl and 2-butene. So in this case, first there is the first step is the dehydration. First step is the dehydration. There is no attacking of the lessened oxygen on the alcohol by using sulfuric acid. So first is going to be dehydration. Second case, then you have to use potassium dichromate. Potassium dichromate and sulfuric acid. What will happen? There is oxidation here. Each of the product contained written here. Then alkene is oxidized to ketone and carboxylic acid in the presence of potassium dichromate and sulfuric acid. Each of the product contains less number of carbon atom than the parent alcohol molecule. Parent alcohol molecule contains 1, 2, 3, 4, 5 carbon atoms. So this will be going to oxidize to get carboxylic acid. Carboxylic acid, CH3, CH, 2 oxygen you add here, and then other product is a ketone. And you can see here CH3 and oxygen will be added here, and CH3, 2 oxygen are going to be here. So it means that how many oxygen you add total? 3. 3 oxygen you need here. 2 oxygen you need to make a carboxylic acid and 1 oxygen you need to make a ketone. So there are 2 steps here. There are 2 steps. In first step, there is the formation of dehydration in the presence of sulfuric acid to make the alkene here. This is the first step. In the second step, there the cleavage or double bond. This portion is going to be broken down in the presence of potassium dichromate and sulfuric acid, and this is the lessened oxygen going to produce 3 atoms of lessened oxygen, 2 atom oxygen combined to make a carboxylic acid here, and 1 oxygen is going to be formed a ketone. So 2 products you will get in this case. So this is the oxidation reaction. So again I am telling you, primary alcohols oxidize to give aldehydes and then further to give a carboxylic acid. Secondary alcohols give ketone. Tertiary alcohols resist to oxidation. First they react with the sulfuric acid as a dehydrating agent to make alkenes, and alkenes then in presence of concentrated sulfuric acid and potassium dichromate to give 2 products. One is called carboxylic acid and second is called ketone. So this is the oxidation of alcohols. After oxidation of alcohols, there is a phenol, carbolic acid, phenol. Phenol. We call it carbolic acid. So, introduction about the phenol. First prepared by Rung, R-U-N-G. Melting point of phenol is 41 degrees Celsius. Boiling point of phenol is 182 degrees Celsius. We call carbolic acid, and formula is arene, C6H5OH. We call, there should be arene, aromatic. This is a phenol. Aromatic compounds containing one or more hydroxyl groups directly attached to the carbon-benzene ring are called phenols. The simplest example is phenol, which is also known as carbolic acid, C6H5OH, already I wrote on the board. It was first obtained by the Rung in 1834. Phenol is derived from the old name of benzene, we call phen. Old name for the benzene called phen to include the suffix that indicates the possesses a hydroxyl O, that's why we call phenol, phenol, yes. Phenols are slightly acidic in nature. Phenols are slightly acidic in nature, important intermediate in the preparation of the ethers. Nomenclature. In the nomenclature, you have monohydroxyphenol. This is the monohydroxyphenol, and if you are going to put more hydroxyl groups, this is the one hydroxyl group, and if you are going to put in the artho position, 1, 2, 3, 4, 5, 6, or you can start from here, one stem. So if the two hydroxyl groups are attached with a phenol, so we call 1, 2 dihydroxybenzene. 1,2-dihydroxybenzene, or this is a reference, already I told you in the previous lectures, and this is the artho position, so we called artho hydroxylphenol. Artho hydroxylphenol. And the common name is called catch coal. This is one thing. If you change the position, here, so this is a 1, 2, 3, 4, 5, 6. So this will be a 1, 3 dihydroxy benzene, or you can say meta hydroxyl phenol, and the common name is called resorcinol. Resorcinol. This is the common name. This is the Ayurvedic name. This is a common name also. You can do this one. And if you are putting the para position here, so this is called 1, 2, 3, 4, 5, 6, 1, 4 dihydroxy benzene para hydroxyl phenol, and the common name is hydroquinone. Hydroquinone. In the ortho position we call catechol. In the meta position we call resorcinol. In the para position we call hydroquinone. You should know these one. So if these are the same, these are the same positions in nomenclature. Now if the different groups are attached, different groups, so nomenclature for the different groups, suppose we have this is a OH and this position is nitro. Dear students, while you are giving the names, so I'll tell you hydroxyl is more reactive than nitro. To make the hydroxyl group reference, starting number from here and making the reference of this OH group. So 1, 2, 3, 4, 5, 6. So this will be a 2 nitro phenol or ortho nitro phenol, like this. And if you put here, then it is called meta nitro phenol, then para nitro phenol. Okay. If like this one, 1, 2, 3, 4, 5, 6, 2, 4, 6, try nitro phenol we call picric acid. So these are the nomenclatures of the phenols. Then structure. The alcohol functional group consists of oxygen atom bonded to an sp2 hybridized aromatic carbon atom and hydrogen give via sigma bond. sp2 hybridization. Both carbon and oxygen hydrogen bonds are polar due to the high electronegativity of oxygen atom. Conjugation exists between an unshared electron pair on the oxygen atom and aromatic ring. The result is, compared to the simple alcohols, a shorter carbon-oxygen bond distance, or more basic hydroxyl group, or more acidic hydroxyl proton OH group. I told you that is a crystalline form, 41 melting point, 182 degrees Celsius, it's a boiling point. It's the less soluble, sparingly soluble in a cold water to give a pink solution. And when you increase the temperature, so it is going to be completely soluble at 68.5 degrees Celsius, which is called upper consolate temperature. So this is in the first year you done phenol water system, and it is a poisonous. We use as a disinfectant. It is used as disinfectant in washrooms, and it is a disinfectant order also. So there is a nomenclature, structure, and now physical properties. Now comparison of acidity of phenol, alcohol, and carboxylic acid. So now acidity. Acidity of phenols. Phenols are more acidic. Phenols are more acidic. Value of pKa for the phenol is less, means approximately 10. pKa value for the phenols approximately 10, and for the alcohol approximately 16 to 20. Less the value of pKa, more the acidic in nature. Less, but it is going to be less acidic than carboxylic acid. pKa value for the carboxylic acid is about 5. So carboxylic acid is more acidic than phenol. Phenol is more acidic than alcohol. Carboxylic acid pK value is 5, more acidic. Phenol is about 10, more acidic. And the least one is alcohol, which has a 16 to 20 pKa values. Carboxylic acid, there is one order I have written: carboxylic acid, acetic acid, then carbonic acid, then phenol, then water, then alcohol. Carboxylic acid, carbonic acid, phenol, water, alcohol. Comparison of acidity of phenol and alcohols. The stronger acidic nature of phenol than alcohol can be explained as phenol exists as a resonance hybrid of the following structure. Phenol. How the bond, the pi bond is going to be shifting. This is number 1, phenol, resonance. This is a sign of resonance. Second, This is the second one. The second. Third. Now students, when I am going to shift double bond here, this is a carbon and this carbon has a double covalent bond, and there is a bond between oxygen and hydrogen. So the valency of oxygen is going to be increased, so positive charge is created and there is a lone pair. So that's why the valency of this carbon is going to be increased. So lone pair is created here and negative charge here because bond is going to be shifted. This bond is no more like this one. So this structure can be changed. This structure can be changed because this bond is shifted to here. This bond is shifted to here. The valency of oxygen increases, positive charge is created. Valency of this carbon is not satisfied, negative charge is created here. So this is a structure number 3. Number 4. In the number 4, now this bond is reverse back, this one. This bond is going to be reverse back here. So it is going to be make double bond here, reverse back here. So lone pair electron and negative charge is going to be created here. So this structure is number 4. 5. Now in number 5, now this bond, this is going to be shifted to here, back here, like this one. Already bond here, and this bond is going to be shifted here. There is another position. Like this one. So this is another phenol. We have the unpaired electrons. So there are 5 different resonance structures of phenol. So thus, due to the resonance of oxygen atom of the alcohol H group acquires positive charge as the structure 3 to 5 positive charge. With the electron pair bond leading to release of hydrogen atom to proton, we call phenolate ion. Phenolate ion or phenooxide ion. Phenolate ion or phenooxide ion is going to be formed here. So carbon atom of COH. In phenol is sp2 hybridized. COH is a sp2 hybridized. is more electron attracting. This is the reason. It is a more electron attracting than sp3 hybridized carbon atom in alcohol. Carbon oxygen hydrogen bond in phenol has more attracting power, which is a sp2 hybridized, as compared alcohol, which is a sp3 hybridized. Thus, in phenol there is a greater inductive effect, which facilitate proton release. So, release of proton facilitate sp2 hybridization between carbon, oxygen, hydrogen and phenol. More effect of releasing protons. The proton donor is called an acid. It is going to be donor proton. So thus the phenol are more acidic than alcohols. This is the reason that phenols are more acidic than alcohols, because carbon, oxygen, hydrogen bond, and there is a sp2 hybridization. In alcohols there is a sp3 hybridization. So in the phenol they have a more electron attracting than the sp3 hybridized the carbon and alcohols. So the phenol can release the proton easily as compared alcohols. That's why they are more acidic than alcohols. So since resonance is impossible in alcohols, there is no resonance due to the absence of conjugated of the lone pair electrons of oxygen with double bond. Alcohols have no resonance structures. In absence of conjugation of lone electron pairs of oxygen with double bond, the hydrogen atom is more firmly held to oxygen atom in the alcohols. Hence, alcohols are in neutral nature. So, there is no release of proton easily. The negative phenol ion, this is a phenol oxide ion, negative, are formed after releasing of proton from the oxygen and hydrogen present in the phenol, more resonance stabilized than the phenol, since there is no possibility to delocalization of negative charge in the alkoxide, means in the alcohol. When the hydrogen is removed, you have alkoxide ion. The latter is not stable. Hence, alcohols have no tendency to form alkoxide and hydrogen ion. Not easily alkoxide is formed by the alcohols, but phenoxide is easily formed from the phenols. So we concluded that phenols are more acidic than alcohols. Phenols are more acidic than alcohols. So dear students, we stop here. Then we will inshallah study comparison of acidity of alcohols with carboxylic acid. This is the next topic, and we completed the properties of alcohols, means reaction of oxidation in the different conditions, and then started the phenols. Then this is a very important topic, acidity of the phenols, and how a phenol is going to be shifted the electrons from one position to other position to give different structures of phenols, and how the phenol is more acidic than alcohol. This is very important. The next time inshallah we will study the comparison of acidity with the phenol and carboxylic acid. Definitely carboxylic acid is more acidic than phenol. This is the result. Thank you very much.